100 times more torque. From one steel cup that visibly bends. No stack of gears, no gearbox the size of your fist. Here is the trick, a single flexing gear and almost zero backlash. A humanoid joint has to do two things that fight each other. Hold a heavy pose without wobbling, and hit the exact same spot every single time. Ordinary gearboxes by strength by tolerating SLOP, the tiny gap between meshing teeth called backlash. On a robot arm, that gap is fatal. A little play at the shoulder becomes a big miss at the hand. Errors stack down the limb. Start at the beginning of the chain. Electricity goes into a motor. The motor makes twisting force. That force runs through a gearbox, and the gearbox drives the joint. So why not skip the gearbox and bolt the motor straight to the arm? Here is the problem. An electric motor is fast and weak. It loves to spin, often past 3,000 turns a minute, but it barely pushes. A robot joint needs the opposite. It has to turn slowly and shove hard, enough to lift a limb and hold it. Something has to translate between those two worlds. That is the gearbox's only job, trade away speed to buy torque. Think of it like low gear on a bike going uphill. You pedal fast, the wheel turns slow, but suddenly you can climb. The trade is measured as a reduction ratio. A 100-to-1 reduction means the output turns 100 times slower than the motor, and pushes with roughly 100 times the force. Big number, small motor. But every gearbox has to pay for that ratio somehow. Most pay in backlash. And that raises the real question. How do you get 100-to-1 without any SLOP at all? Now open the box. A harmonic drive is only 3 parts. First, an oval plug called the wave generator. It sits on the motor shaft and it is shaped like an ellipse, not a circle. Second, a thin steel cup with teeth cut around its outside rim. It is flexible on purpose and it is called the flex spline. Third, a thick rigid ring with teeth on its inside, the circular spline which holds still. Here is the move that makes the whole thing work. Push that oval plug into the flexible cup and the cup cannot stay round. It bows out into an ellipse too. And because it is now oval, its outer teeth only touch the rigid ring at the two far ends, the pointed tips of the ellipse. Everywhere else the teeth pull away and float free. So instead of one solid gear grinding on another, you have a soft cup being squeezed into a shape, and that shape decides where the teeth grab. Spin the oval plug, and the two grab points chase it around the rim like a wave running around the edge of a pond. The steel itself is bending over and over, and that bending is what moves the load. That is why engineers call it strain wave gearing. The deformation does the work. Which leaves one thing unexplained. How does a wave running around a rim turn into a 100-to-1 slowdown? Here is the clever part, and it is almost a magic trick with counting. The flexible cup has slightly fewer teeth than the rigid ring around it, exactly 2 fewer. Say the ring has 200 teeth inside. The cup has 198 on its outside. Now watch one full spin of the oval plug. As the wave sweeps all the way around, the cup's teeth mesh, release, and remesh with the ring. But because the cup is short by 2 teeth, it cannot keep up. Every complete turn of the plug, the cup slips backward by exactly 2 teeth against the ring. 2 teeth. That is the whole secret. The plug turns a full circle, and all that motion boils down to the cup creeping backward by 2 teeth out of 200. 2 out of 200 is 1/100th of a turn. So the input spins once, and the output moves just 1% of a rotation. That is a 100-to-1 reduction, the exact number from the start, and it came from a single stage. 1 cup, 1 rings, 1 ovals. Compare that to the usual way. A planetary gear set, the little sun and satellites set up in most drills, cannot reach 100-to-1 in one bite. It has to stack 2 or 3 stages, one feeding the next, getting longer and heavier each time. The harmonic drive gets there in one flat slice by counting teeth instead of stacking gears. But strength and a big ratio were not the hard part. Killing the SLOP was. So where does the near-zero backlash come from? Look again at those 2 contact zones at the ends of the ellipse. At each one, dozens of teeth are meshed at the same time, 30 or more together on both sides of the cup at once. A normal gear only has a couple of teeth touching at any instant. With that many teeth locked in, there is simply nowhere for the parts to jiggle. On top of that, the cup is squeezed against the ring under constant pressure. Engineers call it preload. It is held tight against the teeth before any load even arrives. So when the motor reverses direction, there is no free gap to snap across first. The teeth are already pressed together, so motion transfers instantly. Put those 2 things together, a crowd of teeth in mesh and no slack to take up, and you get repeatability measured in arcseconds. An arcsecond is 1/3600th of a single degree. That is the property that lets a robot hand reach out, come back, and land on the exact same point thousands of times in a row. Precise enough to thread a needle over and over. So here is the full picture clicked together. One thin steel cup, deliberately bent into an ellipse, does 3 jobs at once that used to need a whole stack of parts. It delivers a 100-to-1 reduction. It multiplies torque about 100 times. And it does it with almost zero backlash. all in one flat, light, compact slice you can tuck inside a joint. That combination is exactly why the harmonic drive became the default gearbox in humanoid robots and precision robot arms. Strength and accuracy from bending a gear on purpose. But nothing is free, and this design pays a real bill. That cup flexes millions of times, so metal fatigue sets a limit on its life. It eventually wears out. It costs more than a plain planetary gear set doing rough work. And because the steel is springy, the output has a little give under heavy load. Twist hard and it flexes a hair before it holds. For a robot that has to be exact, engineers accept that trade every time. A gear that bends beats a gear that slips. Next time you see a humanoid robot hold a cup without crushing it, you will know the trick. Bending a gear on purpose is how it gets strong and precise at the same instant. Want the rival design? Cycloidal drives chase the same goal with a completely different move. That is the next box we will open.